All right, so our first lab in Gen Chem 2 is going to be about electrons jumping around. So what does that mean? Well, electrons can reside in energy levels that we give numbers of n, right? So we're going to think about electrons jumping up these steps. And so I want you to envision that as jumping up or down a staircase. And one thing that's really unique about these staircases is that the energy levels between the stairs are uneven. So imagine a staircase where the first jump is very big and then the next jump is not as big, and the jumps eventually get smaller and smaller. And so things to think about as we think about electrons jumping around, just like you might imagine jumping up or down stairs, is if you are starting at a low stair, a low energy stair, and you are going up to a higher energy stair, you imagine that you'd need to input energy into that system. And like if you were to imagine jumping between a fixed level of stairs, you'd like to match the amount of energy that you need to jump up that stair so you land on there perfectly. You don't put more energy in and you don't have not enough energy, so you don't hit that stair. So conceptually, that's going to allow us to think about these fixed amounts of energy that allow electrons to jump between these different energy levels. And so we're always going to be starting or talking about a level that we start at initially and then end at finally. So we'll say start and stop, but some terminology that's going to be important to think about as we talk about energy differences is final and initial states. We'll get back to that in a minute, but we're going to talk about energies going uphill, and that's going to require us to input energy. We also can think about going in the reverse direction, where if we start out at a higher energy level and then that electron jumps down, then that downhill energy sort of transition allows us to output energy. And again, it's going to be a fixed amount of energy depending on what energy levels that electron is jumping around between. So I'm going to use that analogy a lot, talk about electrons jumping back and forth between levels. So we're going to actually see this in an application sense in lab, and you'll spend a lot of time in lecture thinking about the theory behind this and doing more calculations based on this. Okay, so we can define the energy level of each of these stairs using this equation. Now, you don't need to worry about this is a constant, it'll be provided for you, but this is the important piece. It's a reciprocal of the square of whatever energy level you're at. So we're going to be able to determine the energy levels of each of these stairs, and if we know the energy levels of each of these stairs, we're going to be able to determine the energy that it takes to jump between them. And we're going to call that this delta E. And anytime we see delta, delta means a change or a difference between. And we always want to be thinking about final minus initial. So our ending state minus our initial state. Okay, and if our ending state is higher in energy, okay, larger number minus smaller number means we're going to have to put the difference of that energy in. However, on the other side, if we are jumping down, then whatever energy we get is going to be output. So again, energy input is going to allow us to go uphill. Energy output is going to allow us to go downhill. And so if we take the differences in the energy levels of these different levels, we can determine how much energy we either need to put in to jump between different energy levels or will get out as we jump down energy levels. Okay? So one of the other things we can do in an equation you'll see in lecture and then we'll use here in lab is if we know what this energy gap difference is, we can use this equation to determine what wavelength of light that corresponds to. And if you haven't yet gotten to this in lecture, that's okay, you'll be getting to it soon. But this equation allows us to relate the energy to a wavelength of light. H and C are just constants. H is Planck's constant. C is the speed of light. So those are fixed numbers. And so these are two variables that we're interested in, correlating the energy difference with a wavelength of light. Now, one of the interesting things that we'll see in today's lab is those wavelengths of light oftentimes can be determined by instrumentation or instrument methods, but sometimes we actually might be able to use this instrument, our naked eye, if the wavelengths of light fall between 400 and 700 nanometers, which is the visible spectrum. Okay, so all the colors that we see correspond to a very narrow range of what we call the electromagnetic spectrum. Okay, so let's talk about what you're going to be doing in lab today. two-part lab. The first part has to do with the hydrogen spectrum. There's kind of an A part and a B part to this lab. The first part is a bunch of calculations that we need to do. In reality, what you're going to be doing is calculating what these energy levels are, kind of the energy levels of these steps, and then you're going to calculate the 10 gaps for all of the jumps that we could possibly be doing between stair number 1, stair number 5, and everything in between. Okay, so the first part is a calculation-based piece. Okay, you're going to calculate the first 5 energy levels of the hydrogen atom. So again, that's what are these 5 N values? So it's really putting in those different N values and calculating what E is. So you're calculating the energy levels of those steps. Okay, so there's on page 4, there's a place for you to actually do those calculations. And then on page 5 of your handout, there's a diagram where you actually fill out what those energy levels are. You need to check with your instructor and make sure that those values are correct before you move on to the next step. There's a spot for your instructor to initial your work there. So that's the first 2 questions. Third question now is calculating delta E for the 10 possible transitions. Okay, page 4 again has a spot to do those calculations. I'd encourage you to think about doing a systematic way for determining this. For example, 5 to 4, 5 to 3, 5 to 2, 5 to 1. Okay, and then 4 to 3, 4 to 2, 4 to 1, 3 to 2, 3 to 1, 2 to 1, and so forth. So think about a systematic way of identifying all 10 of the possible sort of jump transitions that we could have. And once we know the energy levels of these 5 steps, taking the difference of them, right? The difference of them will give us the energy levels between those steps. Okay, so that's this third question. So lots of calculations kind of doing this initial part here in part A of this hydrogen spectrum piece. Okay, the second part is actually doing some observations. Okay, so here's what you're going to do. You're going to have this little, looks like a little telescope that you're going to be looking through. It's called a diffraction grating. And what you're going to be doing is you're physically going to be looking through that diffraction grating and looking at 3 different kinds of lights. We're going to look at an incandescent light bulb, right? Those are sort of the old style sort of light bulbs that have a filament in them. Then you're going to be looking at fluorescent light. And then you're going to be looking at the hydrogen spectrum, so looking at a hydrogen lamp. Okay, now all of these, we're just going to be making observations about what you see. And I'm not going to kind of like give you any hints right here. I want you to see it as you're going to see it, but you're going to write down observations for what you see. And then on page 6, you're going to see that there's a space where you are going to write down, you will actually see 3 to 4 specific lines of a defined color. Okay, and then what you need to do is on page 6, you're going to relate calculations from page 4 to the observations that you see with that hydrogen spectrum. And here's what you're going to do, right? You're going to take the color that you see, and based on the fact that if you see color, it means you are seeing something in the visible spectrum. Okay, so you are going to infer a wavelength of that light. Okay, based on calculations that you had, right? Knowing that anything that's purpley is towards the 400 range, anything that's red is towards the 700 range, and then you're going to assign that to a specific transition that you know matches that wavelength. Okay, that's confusing, don't worry about it. We'll address that again once you get to that point in lab. But it's sort of connecting together these 2 pieces. Okay, and that's the hydrogen spectrum part. Okay, the last part is you actually get to use a fire, and you're going to light some solutions on fire, and you're going to see if they make a color. Maybe you already know about some of these things that can happen. You can buy these little packets like at the camping store, right? Little things that you can put into your campfire, and they'll make your campfire turn all fun colors. Fireworks are an example of this phenomenon. Just when you are, let's say, boiling pasta and you've got some salt water that kind of boils over, all of a sudden the flame turns a different color if you're using a gas stove. This is all sort of part of the same sort of process, which is we can use heat or energy from heat to force this electron jumping. So what happens when you put some of these electrons in a flame is we force them to jump up a level, and then when those electrons jump back down, they release light. So we call this forced jumping. We put them into an excited state. So electrons get put into an excited state, and then when they relax back down, that energy gets given off as light, and often it's light that we can see. Okay, so this is going to be the second part called flame analysis. Okay, it's going to be a qualitative sort of part of the lab. All we're doing with this is observations. So here's how this works, and we want to make sure that people are not only safe, but you know exactly what you're doing with this. There are going to be 5 salt solutions. Generally, they're nitrate or chloride solutions, so we've got a spectator ion we're not worried about, but we've got metal ions that are going to be excited by putting them in heat in a flame. Okay, so you're going to have some test tubes here. I'm going to highlight, make sure you clean out your test tubes really well. It'll just take a couple of minutes and it'll save you making sure you don't get dirty answers because you've got contaminated test tubes as we sort of move through this step. So clean out your test tubes. It's totally fine if there's water that's still left in there, but we just want to make sure that when we put 10 drops of these individual solutions in your test tube, that's the only ions that are in solution. So you're going to obtain samples. Okay, you're going to have 5 samples that you're going to look at, and you're going to do these samples one at a time. So here's what you're going to do. We're going to have a special wire that we're going to use that we can put in a flame, and we're going to see what happens. So here's what you need to do sort of before each sample that you're going to check. You need to make sure that that wire is nice and clean. If it looks like it's got some residue in it, there should be a hydrochloric acid solution that you can sort of dip it in. Make sure to sort of remove any residue that's on it. Rinse it off, and then to make sure that there's no metal ions that are left over there from another sort of trial, you want to clean the wire by putting it in a flame. We're going to be using Bunsen burners, so you want to make sure that you heat that so that it's sort of red in color. It looks like hot metal. And then importantly, let this loop cool. Okay, shouldn't take more than a minute, right? But we want to make sure that that metal is cool before you put it in your sample. Then you're going to take one of your test tubes that has that 10 drops of that liquid in there. You're going to dip your wire in there, just getting a little bit of that solution on the wire, and then you're going to put it back in the flame, and within the first 5 seconds, you're going to look for an observable color, and then there's a spot on page 6 for you to record these observations. Again, totally a qualitative part to this lab. Shouldn't take very long to do, but it can make sure that you've got clean samples to work with. And you're going to record these observations, and you're going to see which ions make different colors. And that's our lab, our first lab here, kind of looking at how we get electrons to jump around.